Brian, welcome to the Astroben podcast. How are you?
It's great to be here, Ben. Thank you for inviting me.
Oh, thank you. As you well know, I've been trying to get you on for a while now. I'm somewhat of a fan. I'm not ashamed to say it. So the honour is definitely mine. So thank you for jumping on. Um, I'd love to jump straight in there to talk about you, if that's okay. So let's
My
start
favorite
talking about
subject.
your. You've got, there you go. Let's talk about your book, Losing the Nobel Prize or Nobel Prize. I'm not even entirely sure how to pronounce it. Um, Tell me about it. I'd love to hear your sort of interpretation of it, how the idea came about, and crucially about the bicep
Yeah,
experiment. Would love to hear, yeah, a little synopsis.
sure. So I think there's way too many books in the universe. I think that there are books written because someone says, "Oh, that dish you made on Friday night was really delicious. You should write a cookbook." And then the cookbook comes out, or you really had this wonderful blog post, and it could be a book. It's so interesting. And so I resolved to never write a book unless I was the only person on earth that could write such a book. In other words, that was kind of my algorithm and my rubric for ever deciding to write a book, which I didn't ever envision doing. And now I've produced three books, so I didn't really take my advice, or maybe I thought I am the ideal person three times to do it. And I think the latter, with all humility, which I can muster. So the first book is Losing the Nobel Prize, and it was a story as a memoir of being a young scientist, of aspiring to win the greatest accolade, not just in science, but in all of humanity, which is the Nobel Prize, and to do so for good purposes and for slightly not nefarious, but for purposes that are not altogether altruistic, which was the fame and the attention and the prestige and the enduring legacy that only the Nobel Prize conveys in society at present. So it was a mixture of wanting to understand the universe. That was kind of the pure altruistic motive that I've always had since I was a young child. And I got my first telescope at age 12, and I've only and always been interested only in the biggest picture topics that one could study. And so that was done altruistically, creating the experiment, and but pursuing it with the doggedness that I did and the fierce determination that resulted, which is the bulk of the book, Losing the Nobel Prize, was really done in part to as part of a competition with both personal figures. My father was a great scientist, but we had a huge rivalry, and he never won the Nobel Prize. He won other awards, and I always wanted to kind of one up him, as kids might do in the UK with cricket. They want to be better than their dad at football or cricket or whatever. Here, for me at least, I wasn't very good at cricket. I never hit a century like my hero Michael Atherton, but in the other kind of sense of the word, I wanted to outdo my father, and that was to win a prize he never won. That was one motivation, and the pure motivation kind of eventually took over, and I think led to the actual production of the book. I saw what the pursuit of essentially what is academia's and society's highest idol was really driving a lot of unforeseen and undesirable consequences for individuals, for groups, and for science as a whole. And so it's partially, kind of a warning or a Jeremiad and a memoir of aspiration, of coming close to success and by this metric, but ultimately coming up short of the promised land that I hope to enter, and advice to young people in particular on how to balance the real meaning of life with the pursuit of with wisdom as an adult scientist. So that's really what it was written for, and it tells the story of an experiment that I helped to create called Bicep 2, which is a cosmology experiment designed to look for the earliest light in the universe, called the cosmic microwave background radiation, which is a form of photons that are in the microwave regime of the electromagnetic spectrum. And I know your audience is the second smartest podcast audience in the world, and so they know probably many of these terms. But I'll humor and I'll beg the indulgence and forbearance of your erudite listenership by saying that in the universe, the most likely photon you're likely to find is a photon resulting from the fusion of the light elements on the periodic table called the cosmic microwave background radiation, the leftover heat from that process. And that photonic signature is a relic, like a fossil that's traveled through space, traveled through time, like a fossil does to a paleontologist, and came into our laboratories and our telescopes, in this case, a telescope based on refracting telescope technology with advanced technology like superconducting quantum sensors, located at the South Pole, Antarctica, where I spent, over a month of my life in designing, building, deploying, and then analyzing the data along with my graduate students and postdocs and my collaborators from Harvard, Caltech, Minnesota, Stanford, and all the top universities around the world. And it culminated with an announcement in 2014 that we had indeed discovered the earliest fossils of the Big Bang's history, which was an aftershock of the process that ignited the Big Bang called inflation, or so we claim. And this signature, if true, would have meant not only did the universe begin expanding because of this type of quantum field called the inflaton, but also that a paradigm known as the multiverse prevailed, that we actually are just one universe out of a possibly infinite number of multiverses, of universes within a multiverse. So the astonishing conclusion was printed on newspapers around the world and television shows or CNN, etc. And that was that we had, surely been capable of detecting the signal, and if it were confirmed, we were all going to win Nobel Prizes. But of course, spoiler alert, the book is called Losing the Nobel Prize. So not only did I not win it, but none of us won it. And in fact, the result that we announced was incorrect. The interpretation was incorrect. The data were absolutely flawless and beautiful. It was the interpretation that we had seen this aftershock event of the inflation process. That was incorrect. We had actually seen something very different. And that is sort of the theme that runs through the book, and a warning to young scientists, again, to beware of what's called confirmation bias. When you seek something as a scientist, as Richard Feynman said, you have to be careful that you don't fool yourself and simultaneously know or believe that you're the easiest person to fool. And we kind of played that role, that we wanted to see something, and so we took all pieces of evidence that confirmed it, put it together, and didn't wait for evidence that could have contradicted our conclusion. Again, the data are correct, but the conclusion was incorrect. And so later, data came in, and we had to retract our conclusion that the universe began with inflation. So now it's an open question that my colleagues, former colleagues on BICEP, I'm no longer a member of the team, but current colleagues on the Simons Observatory, which I co-lead, those projects are still searching for this signal. So it's quite a hot topic still in science, because if detected, we would be detecting the earliest physical evidence in the universe's history. And as I said, evidence for the multiverse. So what could be more exciting than that?
That's fascinating. Such a great synopsis. Thank you. Just thinking about the sort of moving away from the book and thinking about the, trying to ask the big questions and looking back to the origin of the universe, the recent images and data of the James Webb Space Telescope. Has that told us anything in particular? I know in the last couple of weeks they've shown images that are, I think, 400 million years old since the Big Bang, which seems remarkably close. What's your interpretation of the reported findings so far?
Yeah, so what they've shown are not images that are 400 million years old, but 400 million years after the Big Bang. So actually, we believe the universe is about 14 billion years old, meaning that these galaxies were produced 400 million years after the Big Bang, means 13.6 billion years ago. And just to orient you, the Milky Way galaxy might only be half that age, and the sun is certainly only maybe a third of that age. So it's quite astonishing that there were galaxies, which are agglomerations of stars in vast assemblies, some with redoubtable structure, like spiral structures, only a few hundred million years after the formation of the universe, suggesting that the universe is remarkably efficient at generating cosmic structures. And so this is potentially revolutionary for a variety of reasons. It has been used, unfortunately, by some folks. I've had a running, not in-person debate, but a running debate on my YouTube channel and his YouTube channel. His name is Eric Lerner, who claims since the 90s, and probably before that, that the Big Bang never happened. In other words, he's using the evidence of structures that are advanced, that are sophisticated structures like rotating spiral assemblies of galaxies. He's claiming that that can't happen in just 400 million years. Therefore, the universe wasn't created or established 400 million years earlier. In fact, it's been around essentially forever. So he claims the universe is static, there was no Big Bang. So some people are using these data from Webb in a rather suspicious way from the majority of actual practicing scientists. So he is not an astronomer by training. He doesn't have a PhD, but he does have a substantial online following on his YouTube channel. You can check out, your listeners can go check out his channel and my 2 videos about him. But the bottom line is the data have nothing really to say about the Big Bang occurring or not, but rather they upend some of our understanding of what happened afterwards. The Big Bang doesn't say anything about how galaxies could possibly form. But the model that then suggests how the universe evolves under the influence of gravity does have something to say, or does get impacted by the results of the James Webb Space Telescope that you are highlighting. So that may cause a reevaluation, for example, of the forces that are responsible for gravity, namely dark matter predominantly is the most important form of matter energy in the early universe. It has to do with the universe possessing about 4 times or 5 times as much energy, mass energy in the form of dark matter. And in fact, at the earliest phase of the universe, dark energy is almost irrelevant. So really the primary player on the scene in the early universe is dark matter. And this is calling into question some of our formation of structure and dynamical properties of objects in the extremely early universe. So it's fascinating and exciting, but it in no way condemns the Big Bang in any sense of the word.
Yeah, thank you so much for clarifying. That's really interesting to hear. And I guess it kind of goes back to what you're saying about the confirmation bias of theories. As new data and new discoveries come out, you have to be humble in the great unknown and have completely, be open-minded to anything pretty much. I had Dr. Julie McHenry on the podcast last week, the project scientist of the Nancy Roman Space Telescope. And correct me if I'm wrong, but I think that telescope will be looking for, using gravitational microlensing, looking for the things that you talk about, like dark energy and dark matter, and the curvature of space-time, etc. Are you excited about that as well?
Yeah, very, very much. That telescope will be phenomenally useful at looking at distant objects, including supernovae and measuring the expansion rate of the universe, and that provides another kind of check, but also a tension, so to speak, in our understanding of cosmology. We have no doubt that all of our models are wrong. Yesterday on Twitter, I put out just a thought that when Michelangelo or Leonardo da Vinci made final brushstrokes on a painting or a sculpture, carved into a sculpture, it's basically done. It may not be, there might be some notion, because art is subjective, that it could be better according to someone's taste. I mean, I've seen paintings here in San Diego, just white canvases, and they go for millions of dollars, and I can't understand it. No, I don't even think I don't even think that they're done. I can't even believe that they even started. It's a blank canvas. But so art is subjective. But when it's done, it's done. Although there are rumors that Picasso used to go into the museum in the middle of the night and put a brushstroke on a painting. And Andy Warhol said that art is never finished, it's only abandoned. But in reality, I think science is never, ever finished. You couldn't even get to the level of a white canvas in science. that we know that our scientific discoveries are quote unquote never complete, they're never finished, they're always provisional. And so understanding the flaws or the lacunae or the gaps in our understanding of our present scientific models is the most, kind of hopeful aspect, the most beneficial and unique aspect of science, is that we thrive when there's a flaw, a gap, a lacuna. We love that because that allows us to go deeper and understand better. If we had just stopped at Newton, if Isaac Newton, your countryman, if he had we stopped at Galileo because Galileo was a very smart man, we would never have the inverse square law or the theory of universal gravitation. If Einstein had said, well, Newton's pretty smart, he's the expert, we should just defer to him, we never would have had general relativity, and we wouldn't have our GPS, kind of time standards and triangulation that are accurate to the nanosecond that GPS corrections need to be applied from general relativity. So we'd be, literally lost even more so than we are at present. So as Richard Feynman, again, Nobel laureate, said, science is the belief in the ignorance of experts, not the expertise of experts. It's that all these experts are ignorant. Some are more ignorant than others.
That sort of brings us quite nicely onto the subject of your podcast and your social channels. Into the Impossible with Brian Keating is the name of your podcast. I'll tell listeners how to follow it at the end of this. Everyone should check it out. It's generally one of my favorite podcasts at the moment. How did you get into it? Because you've had some fantastic guests on, including 11 Nobel Prize winners, funnily enough. I'm sure that was part of the strategy.
Yes.
When was the moment that you decided to be brave enough to do science communication? Because it does take bravery.
Yeah, especially, you're right. Thank you for noticing that. There's a notion that, scientists should stick to the laboratory, stay in our lanes, do what we do best in the laboratory or the chalkboard. And that, in fact, there's almost pejorative sense that if you are, doing stuff outside of those domains, that you're wasting time, or maybe you're not legitimate, or you're not a good scientist. Famously, Carl Sagan was kept out of the National Academy of Sciences in the U.S., which is the most prestigious on earth, because people look down upon his popularization of science, and you see that quite often, and I've heard that too. Luckily, it's not as bad, but someone asked me like, well, how much time did the university give you off to write your book? And I said, -5 Like, they don't give me anything off. They literally told me, Ben, they said, well, we won't punish you if you write a book, but we're not going to reward you. We're not going to give you any, top credit, even though, my podcast is really the first, as far as I know, in the whole University of California system, as well as by far the largest with, 50,000 active daily listeners. The YouTube channel is closing in about 80,000 viewers and followers and stuff. So, no, it is sort of shameful in my mind that we denigrate scientists who do outreach in addition to doing science. If you only do outreach, then you really shouldn't call yourself a scientist that's practicing. And the best example of that is Neil deGrasse Tyson, who has been a guest on my podcast. And he'll admit that he is not a scientist practicing anymore. He's scientifically trained as part of his identity as a PhD. He runs and directs a planetarium that does do research, but he's not at a telescope. He's not publishing papers for decades. So, but he is a communicator. But he makes that very clear. The problem is when you have people that only do one or the other, that say the other should not be done at all, and he'll never do that. So I think it does take courage, as I always say, to go into the impossible, and that's part of the reason we came up with the name for the podcast. I would say that, I started it 5 years ago or so in 2017 because I had an opportunity and an unfair advantage, which everybody should look to in their lives. And that was that I had access to the world's greatest minds that would come through this top university called University of California, San Diego, and they would speak or they would lecture or they'd sign books or they'd do whatever. And I felt, as I was the co-director or the associate director of the Arthur C. Clarke Center for Human Imagination, where we had authors and visionaries and futurists and thinkers, artists, and writers, and they would come through here, and I would say, well, it's great that we get to do an event with 190 people, but it's better if we can scale it to 100,000 people. And the only way I felt we could do that is to record it. And so we started off audio only. And then in 2020, when the pandemic hit, I realized that we weren't getting anybody coming through campus. And that was going to shut down the podcast, except that Zoom or, Riverside, shout out to your host right now, or your production network, that we could do stuff remotely. And that would be good on two fronts. One, it would allow us to feature these great minds and luminaries. Two, it would benefit them because book tours were canceled starting in 2020. And I don't know if they'll ever come back. I think that the publishing industry has now shown that they don't really need them, and they can do these remote interviews and leverage my time and your time and have great authors get their messages out from their books. And that will save them money and also increase the scale of their impact orders of magnitude. I mean, I don't care who you are. It's still going to get more views on a channel like mine or yours eventually. Hopefully you'll put yours out on video because it's just missing a bite at the apple. So you should definitely do that. But it's very hard to grow. And, there's an infinite number of cat videos that are submitted every hour. So it's very difficult to compete with that and TikTok videos, et cetera. But I found it, is kind of my moral obligation as a scientist who's supported by the public to give back to the public for free educational opportunities. And it's also allowed me to kind of display a different component of my personality. As you have undoubtedly learned, there's no one, you don't go to school to become a podcaster. And not to say that you couldn't, I mean, there could be a school to teach podcasting, but podcasting isn't a skill like, changing the oil in your car. It's not a skill. It's not an action. It's a series, a combination of talents, of skills, of different dimensions of your brain, ranging from the intellectual, reading, understanding the book, and then personalities, communicating, and then marketing and publicizing. All these things are micro skills, macro skills. We don't teach them to our students, so I had to kind of learn it on my own. And then the result of that was my second book, Think Like a Nobel Prize Winner, which is the interviews with 9 Nobel Prize winners that I've done in the last 3 years, 2 or 3 years, and putting those all together in a single volume, because it's unlikely people are going to go back and listen to every single episode of the podcast. And I wanted to distill their wisdom, not just their knowledge. So that second book has almost no science in it whatsoever, but it's full of wisdom. And I always say knowledge is not equal to wisdom. So it's almost more important that somebody be wise than they be knowledgeable, because soon, GPT and Wikipedia will outlast us all in terms of knowledge, but wisdom will forever remain the domain of Homo sapiens. In fact, that's what sapien means. It means wisdom, not knowledge.
I like the phrase, knowledge speaks, wisdom listens as well. And I think the fact that you spend hours and hours listening to podcasts, you do become wiser. One of your guests and friends, I believe, that I love listening to is Eric Weinstein, which for those of you that don't know is a legendary figure, managing director of Thiel Capital and host of his own podcast, The Portal. And he's so fascinating to listen to. I feel like I get smarter just sort of listening and probably understanding 10% of everything he says. But I'd like to ask about that actually, his theory of geometric unity. I know you've been sort of quite instrumental in getting the word out there for that. I won't ask you to explain it. I'll put a link in the show notes if people want to go and watch the video. But what's your opinion on that? Is it that taking all biases away from the fact and like the guy, do you think that there's some truth in it? Taking into account I don't really understand it.
Yeah. Well, I think it's important. And I think the reason that's important is because it combines a potentially promising model for reality that incorporates gravity and a theory of everything, along with the three higher energy forces of electromagnetism and the weak nuclear force and the strong nuclear forces. putting those all together is a immense challenge and worthy of a great amount of attention. For the last 4 decades, that attention has been dominated primarily by string theory and an attempt to unify gravity with these other forces. And so it's not only admirable, it has promising features. And even if a model is not the ultimate description, we know, as I said, that, the universal law of gravitation of Newton was not complete, but it got us to the moon. It gets us to the moon every time we send, a rocket there. We don't need general relativity. So even flawed theories or incomplete theories are useful. The question is, what can it uniquely do that is not done by other theories that currently exist? And what evidence could be used to confirm or refute it? And it has to be subject to scrutiny and empirical presentation and refutation. And that's the hallmark of good science. So where I'm interested as an experiment, I'm not a mathematician, I'm not a theoretical physicist, I'm an experimental physicist. So I'm interested in kind of the concomitant predictions that can be obtained from a theory of everything that would bear relevance to the formation of structure in the early universe. Because then I can turn my telescopes and my computers on data and compare with the predictions not only of Eric's theory, but also other candidates, including string theory. And string theory does make predictions. I've had on, probably the most leading luminary in string theory, aside from Edward Witten, and his name is Kamran Vafa, and he's at Harvard. And he's done tremendous work, and he's been on the podcast as well. And we've talked about the predictions, and it's commonly found that people have issues with it because it hasn't been proven. Now, it's been around for 50 years now. Actually, I misspoke, but that doesn't mean that the next 50 years have to feature at all until it has something meaningful or predictive about it. And so I've had on Michio Kaku on my podcast. He's written a book last year called The God Equation, in which he claims that this is the purview of string theory, although we have to supply a lot more evidence to it, and we haven't given it enough time. And it kind of reminds me of the fusion breakthroughs that we're seeing. Fusion has always been called the energy source of the future, and it always will be. And what Michio Kaku often presents is, the grand unified theory of everything of the future, and it always will be. So there's a question of how much dominance it's had and how much impact, positive and negative, it's had on the sociology of science. But where I come in with Eric and all contenders is, how can I provide empirical testing? The math is great, it could be beautiful, but one of my kids today was trying to prove the area theorem for a pentagon, and it was beautiful to watch him do it. And he's like, did anybody ever think of this? I'm like, I'm pretty sure Pythagoras thought about this a couple thousand years ago. But when you do something new, Ben, it doesn't mean that it's new in the history of humankind. It means it could be new to you. And I always say, go and buy yourself a little tiny telescope, even in the middle of London. You can see the exact same things that Galileo saw, but more than that, when you look at the craters of the moon, you'll have the same feeling that Galileo had. Not only the same knowledge and physical sight, you'll have the feeling viscerally that he experienced on that cold, night in 1609 when he first looked at the moon. And then you can look at Jupiter and see that it has these little moons around it too. A tiny $50 telescope. I have a video on my channel called the best Christmas gift you can get, and it's about $50 telescopes all the way up and how that can kindle a love of astronomy and empiricism, just like it did for me as a 12-year-old kid. So the answer to this is that all things must kind of be confronted with data, as I think Niels Bohr said, in God we trust, everyone else must bring data.
And that's such great advice on telescopes as well, because I did exactly the same. Although I must disagree with you. You're lucky if you can see the moon in London. I mean, there is clouds for quite a large proportion of the year.
When it's clear, yeah.
But,
yeah.
I completely get what you mean, and I managed to find the moons of Jupiter, and it was shocking. I wasn't expecting to feel tingles down my spine. It was I think part of the reason was just just pleased that I managed to get the telescope working. But it was you do feel that it sort of it does add that sort of cosmic perspective. So,
Yeah,
you know, you're doing
exactly.
incredible work with science communication, and you know, unlike me, you are a scientist at heart. What areas of research are you currently working on? And also, if you did have a bottomless budget and you could conduct any experiment you want, what would you be doing, given the
Ah,
current
that's
restraints of physics in 2022?
okay. That's a very good question. I'm going to turn it around on you too, because I'm going to ask you if you had an infinite budget for your podcast, what would it look like? But let me first answer your question since you're the host. So my current area of research is still looking at the cosmic microwave background radiation. It's a treasure trove, not just producing Nobel Prizes, but it's producing unparalleled insight into the universe and its composition, its origin, its evolution, and its possible demise. So it's natural because it's the oldest light in the universe, and humans get 60% or 90% of our sensory input comes from our eyes, and so it's natural that we look at light and try to glean as much information as possible. So to do that, I'm no longer using Bicep. I'm not affiliated with them. They're still friendly with me. I'm still friendly with them, despite writing a book that was highly critical of the ultimate leadership and the push to, make the announcement as a press conference rather than a peer-reviewed paper, so folks can read that in Losing the Nobel Prize, as well as a critique of the Nobel Prize itself. But mostly the book is a memoir of what it feels like to deal with colleagues and competitors and ideas and creativity as a scientist, and even suicide and mental health as a scientist. These are all themes that graduate students, postdocs, faculty should be aware of. But it's a memoir for lay people too. So the main focus of my research is still this, but it's now turned from the South Pole, Antarctica, to the Atacama Desert of northern Chile, where I just was last week, and I posted some videos on my YouTube channel there as well, of me going up to 17,200 feet, 5,200 meter above sea level, and constructing a platform and with my collaborators and colleagues from Germany, from the UK. We have a huge buy-in now from the United Kingdom of about 20 million pounds. That's going to be amazing for our expansion plans for the Simons Observatory to build a total now of 7 telescopes. We're going to have 7 telescopes operating, studying 6 of them studying this type of polarization signal that Bicep was aimed at as well, looking for the aftershock of inflation, the spark, as I call it, that ignited the Big Bang. Then we have an enormous 6-meter diameter telescope that is led by my colleague at University of Pennsylvania, Mark Devlin, and that telescope will have unrivaled accuracy and precision in measuring the tiny, tiny details of the microwave background, looking at galaxy clusters, looking for dark energy, trying to measure the Hubble constant, trying to measure the existence of Planet 9. These are all things within the purview of the Simons Observatory, and what will be coming soon will hopefully be as revolutionary as the cosmic microwaves backgrounds, past history has shown us. We have the kind of a big breakthrough, again, kind of parameterized by the Nobel Prizes that we win every decade or so. And I'm hoping and praying this will be one of the, not for the Nobel Prize, I've kind of gotten over that lust that I had, but to actually make these breakthroughs in our understanding of evolution of the universe, but also of things like planets beyond the orbit of Neptune. We can do all that with the Simons Observatory. So that's my goal. If I had an infinite budget, I would certainly build bigger and more versions of the Simons Observatory. And in fact, that's what we're doing. It's already about $150 million experiment. The challenge that we face now is that we really can only build detectors. We can't build detectors more sensitive than my colleague Suzanne Staggs at Princeton. She's designed essentially the most sensitive detectors one could build on Earth. And so the only way to do better is either to put it into space, which could take the rest of my life, or to build just sheer numbers of them more. So you actually can improve your sensitivity not if you quadruple the number of detectors in your telescope, you can actually improve by a factor of 2, not a factor of 4. So it's a slow process, but I would buy, an infinite number of detectors. And then we have these refrigeration systems that cool us down to zero point 0.1 degree above absolute zero, 100 millikelvin. And those are very expensive devices, and we need, hundreds or dozens of those. Each one's about $500,000. Then we need to have the infrastructure at 17,000 plus feet, concrete construction. I would put in a solar power plant instead of the diesel fuel generators we have now. I'd put in battery system so we don't have trucks driving up the mountain like I did. You can watch this video of me driving up there. It's like driving on the surface of Mars, except I'm a New Yorker and it's not so safe when you're with me. So that's my goal. I want to ask you in the couple minutes I have left, if you had if you had a 10x your podcast budget, what would you do with it?
Well, I mean, I think as we've discussed, doing video is something that I should be doing anyway with basically no budget. So that's definitely one of my New Year's resolutions, is to upload the backlog of videos that I have and really try and shamelessly put it out there. But for me, I'd always thought like I need to get to the 100 episode mark, and then I'd sort of feel comfortable in myself doing it, and then I'll start putting money behind it. But I think if there was like any amount I could get, I'd probably want to go to space and take people like you with me. So take on some of my favorite guests, go to space, take up some of the listeners as well, and hopefully inspire by doing that as many people as possible to want to dream of living and working amongst the stars.
Yeah, you truly be. Yeah, you would truly be Astroben at that point.
Yeah, or record a podcast in space, but I'm probably Lex Friedman or someone will get there before me. But until then, I'm happy to sort of be in your, behind you, trailblazing the way, and just enjoying it. I think that's the main thing.
Yeah, that's the main thing, to have fun and enjoy it. Look into a creator in London named Ali Abdaal. He's a very famous YouTuber. He's been very impactful on me and my YouTube strategy. So his recommendation is just get started. Just don't wait for 100. Just start it now, because the best time to plant a tree is 10 years ago. The second best time is now. Just do it now. No one's watching it. No one's gonna care. You're not gonna be ashamed of it because no one will see it. And then by the time you hit 100, post it 100. Then you'll have done an incredible amount. So look into Ali Abdaal and just keep up the great work. Congratulations on everything you've achieved, Ben.
No, thank you. Brian Keating, thank you very much.
Thank you, sir.